Okay, again with no introduction, since this is just a direct continuation. We're going to extend what we've done here with the one-dimensional case where we did this minimization of a parabola, and then we looked at this quartic equation here, to a multi-dimensional case. And I've written out the formula for the gradient, which can be thought of as a generalization of the derivative. This is in 2 dimensions, and because we're going to use the variables x and y later on, I use u and v. So the gradient is just the partial derivative of this function with respect to u in the u direction, and likewise plus the partial derivative of v in the v direction. And you notice that this is a vector quantity. What it does is it gives us the direction of steepest ascent. So in the one-dimensional case here, where we had our tangent line, like our tangent line here, it gives us, because it's a one-dimensional case, it only tells us if the function is increasing to the right or to the left. But down here in the multi-dimensional case, it's more complicated because this plane that you can think of a tangent line as defining the slope of a tangent plane. Excuse me, you can think of the gradient as defining the slope of a tangent plane, and this gradient vector will tell you the direction of steepest ascent. So what we're going to do is the linear regression problem, which we've done before, and I'll put links to the videos in the cards and in the description below. So we're going to take a bunch of, this was just a line plotted here with some random noise added to it, and we're going to try to fit a straight line to it. And just so we can check our answers, I've already done the linear regression. And I know we've done this with various tools like SciPy before, but there's a built-in Polyfit function that'll do the same thing, although it doesn't give us back as much information. So I'm going to use that. I'm going to plot it. And here we go. So we get a slope of a little less than 2 and an intercept of about 0.3. And then I've plotted the best fit line here. So, okay. Remember line equation there of, y is equal to mx plus b, where m is the slope, b is the intercept, and we're looking for the m and b's in such a way that we minimize this square error. So we take all of our data points. So for each data point y sub I and x sub I, we figure out the squared error, and then I'd call this function j. And what we want to do is adjust the m's and the b's as to minimize this function j. And now we need the partial derivatives with respect to m and b, and I've copied those here. This is from our linear regression video, so these are the formulas we're going to use, and we're just going to come down here and code these up as a function. So in the interest of time, I'll just do it. I did this off of the recording, and I also put in this function j, which I called cost function. So this function here is this. We could use it for diagnostic purposes later. And here is our gradient function. Yeah, it takes in our x and y data from this plot here, and just basically calculates out those 2 derivatives. And I just called them fp1 and fp2, just, I don't know, function prime 1, function prime 2. And now this is a 2-dimensional vector, so I return it as a 2-dimensional vector here. So let's run this. Okay. And that's basically all we need to do, since this is just the same as before. We should be able to call our gradient descent function and get out an answer. So we need an initial point. Well, before that, I know I'm going to forget if I don't do it now. So let's just put in our arguments now. The args we have to pass in are going to be x and y. And our initial values, what happened here? There we go. Our initial guess of the minimum, remember this is a 2-dimensional vector, so I'm going to create an array. And I don't know what these are. I'm going to guess -5 and 2. Does that look good? That looks good. Let's make sure there are no typos. There are typos, of course. What am I missing? I need an equal sign. Equals. There we go. So now we're ready for our gradient descent cost. So x0, comma, count is equal to gradient descent. Our function is called gradient, and we're passing in our x0 value, and our args is equal to args. Let's see if this actually runs. Seems to. Let's print out the results. Print x0. So we get minus 1.901 What do we get up here for our slope? 1901 and 3143, and we got down here 3143. Excellent. I mean, perfect. Okay, so next I want to do a simple logistic regression. So what I've done here, there's probably a better way to do this, but I've created a data set. Let me plot this out. That looks like this. Now there are two types of data in here, obviously the blue and the red, and there's roughly speaking a dividing line between the two. And our task is basically to classify a new point given some x and y coordinates. So all this code does is create these data set, and then I stack them into a matrix here. So my matrix capital X is a set of ordered pairs. These are the ordered pairs, and since we're going to need a constant offset term, this is what this ones are here. For the time being, you can ignore this. These are our ordered pairs, and the y vector, the capital Y's, are just a label as to whether these are blue or red. So 0 corresponds to one color, the 1 corresponds to the other. So that's all this code does. So we are going to do the logistic regression now. So let me get rid of that, and let's move on. So one thing we're going to need for this is a utility function. It's called the sigmoid function. I used the symbol g and z because I'm running out of variables to use. So g of z is just equal to this. It's 1 over the quantity 1 plus e to the minus z. So I've coded that here as basically a utility function. And if we just plot it out to see what it looks like, np np.lin space, let's go from -5 to 5. And let's do a plt.plot u comma sigmoid of u, black line. So this is what it looks like. The farther to the negative you go, the closer and closer to 0 you get. And likewise, the farther to the right you go, the more in the positive x direction, you get closer and closer to 1. Let's just do this. Let's go 10, 10. So that's what it is. Okay, let's move on now. So let me in fact just delete this so it's not cluttering things up a bit. Okay, so I fleshed this out a little bit. We're going to represent our parameter vector as theta. In fact, let me change this as to theta equals this. Slash theta is equal to. Okay, so our parameter vector is going to be this column vector here. So theta 1 will correspond to x1 here, theta 2 will correspond to x2 there, and this theta 0 is essentially, it's the equivalent to like the intercept in the linear regression. It's just a constant offset. So we're going to pass this linear model through the sigmoid function here. And then our cost function is just given by this. It's for diagnostic purposes. And our gradient is given by this. A bit of nomenclature here. I refers to the data point. So, it's the ith data point. It's the ith one of these dots. And J refers to the dimensionality of the system, which is, 1 or 2. So it's either x1 or x0, 1 or 2. And I'm skipping over all the details in interest of time. If you want a video specifically on gradient descent or the mathematics thereof and how we're doing this vectorization with this, theta transpose x is equal means, let me know and I definitely can do that. But in the interest of time, I just want to do basically a complicated problem and not dwell on the intricacies thereof. I just want to show that it can be done. So I'm going to code up this gradient, which is what we actually need for our gradient descent, and I will code up the cost function just in case we need it for diagnostic purposes. Okay, so here's our cost function, and I broke each term in here into its own term and then did the summation and the divide by the number of data points here just to keep things simple. This was just in here to make sure that I got all the matrix sizes correct. Same thing for the gradient. It's pretty straightforward. The only thing here is this is to make sure the matrix that comes in for theta is the proper shape. Sometimes some pieces of code assumes that it's a given shape, and if we want to test this with minimize, we have to make sure it's shaped properly. So let's run that. Okay. Anyone want to place a bet on how this works? Let's do it. Let's go. Do I have a theta defined? I do not. So let's say theta, let's call it x0 to be consistent with what we've done before. X0 is equal to np dot zeros. We're just going to make it a vector of zeros, and we're going to make it 3 long. Oh, what's wrong here? NP, how is it not defined? Oh, I shut down the notebook. Let me just rerun all these cells. Okay, there we go. So let's come down here and go x0, comma, count is equal to gradient descent. Our function is called gradient. When I do the when I tidy up the notebook for upload, I'll probably make sure all these functions have unique names for like the linear regression, and that's just to make sure I'm not overwriting everything. X0. Let's just see if that runs. Let's come down here and go print x0 run. We never set up our args, did we? So let's go here. Args is going to be equal to x and y. So we come down here. Args is equal to args. Run. Okay, it seems to run fine. I ran this function through minimize command earlier, so I know that these numbers are not wrong, are not right actually. So let's try to figure out what is going on here. We'll set the debug equal to true, and we'll plot some things out. So let us come down here and we will do theta. We'll use a lowercase j so as not to confuse anything. Let's come here and we will go function. Actually, I used a capital J, didn't I, in my my notes above? Capital J. It's not function, it's f. F is equal to cost, and debug is equal to true. So let's run that. Okay, what's the issue here? Oh, you know what it is. When I wrote that thing to put out the parameters each step, I assumed there was a single value and not a vector. Let me just go and comment that out, and we'll be sloppy in the way we code this, and we'll just kind of delete it for now. Okay, so I commented out those lines. So hopefully this will run now. Still no. What's going on here? Oh, I know. I changed it, but I never reran this cell. Damn it. Where's my gradient descent? Gradient descent. Here we are. Gradient descent. And I'll fix this in the final upload. It's just right now I want to tie a bow on this and get this thing over with. Run. Oh, I need to put in the args. Let me do that. Okay, it seems to be running, so let's just make sure again. We'll run the cell. Come on. Okay, so we get these values, which we saw before, and let's do a plt.plot j. Okay, so you see we never really reach a constant value of this cost function, so we need to add more iterations to it. So I'm going to edit this for speed when we actually run it, but let's do 1,000,000, 1e6. So run. Okay, it finally finished after about 2 minutes, so let's plot this out. Still not great. What are our numbers here? So these still haven't come in. So let's go to 10 million, and I'm going to shut off the recording and just run it, and then we'll see what the results are. So 10 to the 7. Run. Okay, I'm going to say this is good enough for convergence. I've edited out all the adjusting of this. It takes 20 to 30 minutes to actually run this function. So I played around with it on and off for a couple hours and came up with these parameters. So these are our determined parameters, 0.2-ish, 32, 32. That's really not perfect. I wonder if I can adjust this more. I just don't want to waste tons of time on it. Let me give it one more run through and then we'll see. We'll go from there. Okay, so it finally finished after a couple hours this time. Yeah, so these are our parameters, and I plotted them out here. It still may or may not be converging properly, but it's almost there. The thing to note is I had to chop down this J vector several times. So I actually had to run this cell several times. So I've cut down the number of elements in J by probably a factor of 8 to 12 to get it to plot because of memory issues. But yeah, so the last thing I want to do is visualize this by going back to this plot here. Where do I actually plot it? Oh, I've already highlighted the cells. Let me just do it again. And I will plot the dividing line based on these parameters here. So let me plot this just to make sure that it runs. It does. Okay, so now let me plot the dividing line. So I want to go from -1 to 1. So I'm going to say x is equal to np.lin space -1 to 1. Does that run? Yes, it does. Okay, so I worked this out earlier by hand. The equational line will be equal to y is equal to 0.5 minus our first parameter, which is, what did I call it, x0, 0, minus x0, 1 times x, and this entire thing is divided by that last parameter. It would be x0, 2. x0, 2. Does that run? No errors. Let's plot it out. plt.plot x comma y, and we'll make it a black line. Yeah, well, it works, but I went too far with, this should be just 0, shouldn't it? Yeah, so there's our decision boundary. So if it's if the x and y values are in this quadrant, you get a blue, and it will choose red for this quadrant. I know I blew through this logistic regression pretty fast, and there's a lot of details here. I kind of ignored some of these issues, numerical issues that crop up, because you can get potential issues here if you get, for example, one of these logs that return a 0. So if this value here that comes out of the sigmoid function is 1, in this case 1 minus 1 is 0, and log 0 gets an infinity. So you're getting numerical issues, and that's what's happening down here. So yeah, if you want a video specifically on logistic regressions, let me know. I will do so. And I don't know when I'm going to upload the full notebook. Probably by the time this video is up, because there's a lot of sloppy coding in here I want to change, and I want to see if I can refine this not to get these numerical issues. So yeah, I'm not going to do any sort of outro just because this is going on too long. So cool. Until next time, I will see you.